Hi, welcome to today's video lecture. Here we're going to be talking about solving the heat equation in 2 dimensions using what's called the finite difference method, which is an approximation, and we're going to use Microsoft Excel to solve this. So we're going to do a numerical approximation of the heat equation, and we'll be able to solve for 2-dimensional temperature profiles like you see, and we're going to be using a software tool, Microsoft Excel. All right, so just imagine that you have some kind of a beam, a square beam, and if this is this axial direction is the z direction, let's say that whatever we're doing to this beam, it's uniform in the z direction. So this would be a 2-dimensional problem where we would only be concerned about the x direction, which would be coming in and out of the screen, and then the y direction, which would be going from bottom to top. So if we spun this around, we could break this down, again, just looking at this cross-section where we have x going from left to right now and y going from bottom to top. So a way of solving this, if we wanted to know the temperature distribution throughout this, so let's say whatever's happening in the z direction, again, is uniform, so dt dz equals 0. We don't have to worry about how temperature changes with respect to z. Let's say we were, I don't know, heating it or something all along this left-hand side. So we would expect to see some kind of a temperature profile develop, and we want to be able to solve for what does that temperature profile look like. So an approach to doing this would be to take this cross-section and divide it up into a bunch of different control volumes or nodes like this. And then what you could do is you could take an individual control volume like this guy and do an energy balance on it. We did this in class when we went through and derived the heat equation in Cartesian coordinates, except now we're narrowing that down from 3 dimensions down to 2, and we're going to be doing a numerical solution here rather than shrinking this down to differentially small control volume resulting in a PDE. We're going to keep this as a series of ordinary differential equations, and we'll use this finite difference approximation method to solve that. All right, so if we looked at our system and we looked at one of these nodes or control volumes that I just mentioned, we're going to do an energy balance here. So I'm going to call this the I, jth node, where I tells us which node we're in as you're going from left to right in the x-coordinate, and then j tells us which node we're in as we're going from bottom to top in the y-coordinate. So if we go further in x, that makes this one the I plus 1, comma j. It makes this one to the left the I minus 1, comma j. The one above is the I, j plus 1, and the one below is the I, j minus 1. So this is the nomenclature we're going to use as subscripts just to tell us which value are we talking about, and we'll be talking about temperatures. So we'll do an energy balance on this node, and just again, let's remember that we do have a depth here, which we're going to use. Let's just call it z in this problem. We'll use that as we compute volumes or cross-sectional areas. In the x direction, let's say that our node is delta x thick, or delta x wide, and then here it is delta y tall. All right, so let's think about an energy balance on this node. So because this node is completely embedded in our solid, the mode of energy transfer or heat transfer has to be conduction. It's not on an edge where it could be exposed to radiation or convection. It's just purely conduction. And what we're going to be doing here is, if you recall when we solved the heat equation, we shrunk delta x and delta y down to being really, really small. So here, as much computational power as we can, we're going to try and have a high-resolution grid here, which means that we can make this approximation assuming that delta x and delta y are really small. And so when we do that, so when delta x and delta y are really small, we can make this approximation that dt dx is approximately t I plus 1 minus t I divided by delta x. So this is the finite difference approximation of the first derivative of temperature with respect to x. And we'll be doing the same thing in the y direction. So with that in mind, let's define an energy balance here. So we have accumulation In this problem, we're going to assume steady state, so accumulation is going to be 0. We're going to have an in term, we're going to have an out term, and then we could also have generation in this problem, and I've kind of written it out like this for a reason here. So we're going to break this problem down. Energy could be flowing here in the x direction, or it could be flowing in the y direction. And again, we're going to make this at this scale. When you shrink delta x and delta y to be really small down, you can assume that x is just flowing in this one direction and this other direction there. So we don't have to worry about like angles here, because we're just going to assume once you shrink this down, you can break it down into those two coordinates pretty easily. So we're going to do I'm going to go ahead and get rid of our accumulation term. We just know that accumulation is 0 here. And I'm going to break this down to energy in and out in the x direction and energy in and out in the y direction. So energy is coming in the y direction. It's coming from, rather in the x direction, it's coming from left to right. We'll just assume that it's hotter on the left-hand side and flowing that way, just to helps mentally to just envision energy flowing from left to right. But the way that we'll derive this, it could work either way, as long as we stay consistent with our coordinate system. So here, energy flowing in is going to be flowing in by conduction. That's defined by Fourier's law. So here we're going to have minus k. And this would normally be dt dx, but we'll assume that we are dealing with a small enough system that you can approximate dt dx as this ti plus 1 minus ti over delta x. So we're going to plug that in here. And this is still ti plus 1j. Oops, and I messed up here. So energy that's flowing here across this boundary, we're actually going to be using I minus 1. So this is tij minus t I minus 1 comma j. And that is divided by delta x. So we're just looking at energy crossing this boundary. So the driving force there is going to be the temperature difference between node I minus 1 and node I. So that's how we use the difference between those two as our dt dx. So here we would multiply this by our cross-sectional area, which is going to be delta y multiplied by z. So that z doesn't really matter. We could call that L or whatever for the length of this beam, but we'll just stick with z. All right, so going out, now energy would be going here, crossing this boundary. So our out term would be minus k times ti plus 1 comma j minus ti comma j divided by delta x. Again, just as a reminder, we're using this finite difference approximation method. The cross-sectional area is the same, so that's delta y times z. So now in the y direction, it's similar. We can assume that energy is flowing from bottom to top. So when it's, let's say this node is hotter, we'll just make that assumption for this derivation. So here we would have energy coming in is defined by Fourier's law. And so here we'd have minus k ti comma j minus ti comma j minus 1. And now we're going to divide by delta y because our energy is flowing this direction, so y is the pertinent coordinate. And now our cross-sectional area is going to be delta x multiplied by z. Going out, it's similar. Again, Fourier's law is minus k dt dy, so here we have minus k. Now we're going to use these nodes. Energy is crossing this boundary to get out of our control volume. So here we're going to have ti comma j plus 1 minus ti comma j divided by delta y, and here we have our cross-sectional area of delta x times z. So our generation could still be happening in this problem, so let's just define a generation term that looks like this. Q dot, this would be volumetric generation. Q dot would have units of watts per cubic meter. So we need to multiply Q dot by the total volume of our control volume. And so that would be times delta X times delta Y and then times Z. All right, so we've got our energy balance. So we have our accumulation equals in minus out plus generation. When we first plug this in, we're going to assume generation to be 0, but we can have certain nodes that might have generation, which we'll toy around with here in a minute. So we're going to take all of our in terms, and then we're going to subtract off all of our out terms. So once we do minus out, you'll see that these two terms become positive. This is a little bit counterintuitive, where you think of in coming in. It's going to have the negative sign, and then out is going to have a positive sign, because the Fourier's law has the negative sign, and then the minus out cancels that out. Just bear with me here. So what we're going to do is we're going to set up each of these energy balances in Excel by writing them out in equation form. On the left-hand side, accumulation is going to be 0. So we're going to set this up so that we are solving for the right temperature profile that satisfies this energy balance such that our accumulation term equals 0. So I'm going to hop over to Excel and show you. I've got this little template set up already. So over here I have some constants. Z I'm just using as 1. If you did the math, Z would just drop out of every equation. So, but we're just going to assume a basis of Z equals 1 meter. We are going to assume that our system is, in terms of Y and X, we're going to assume that it is 10 centimeters wide and 10 centimeters tall, and then we're going to divide that up into 10 in each direction. So we have 10 nodes going from left to right and 10 nodes going from bottom to top. So in total we have 100 different nodes. So we're using 100 different control volumes to represent our space. So because it's 10 centimeters wide in total, so when we divide that by our number of nodes, that gives us 0.01 meters, and similar in the Y direction. We're going to be using a thermal conductivity in this problem of 2 watts per meter per Kelvin. Here's a generation term of, so that is going to be 5 million watts per cubic meter. If we do use convection, we have a heat transfer coefficient here and an ambient temperature here. All right, so what we're going to do, so I've sort of mapped out our system here. So we've got two things here. We're going to be solving for unknown temperatures here. And we're going to be, so our temperatures will be the unknowns. And then we're going to generate 100 equations representing the energy balance of each of those nodes. So I've got kind of parallel systems here where we have, here's our unknowns go here, and here's where we write out those energy balances. One difference that I want to point out is when we derive the heat equation, you shrink delta X, delta Y, and delta Z down to be infinitesimally small. In this case, we're stopping. We're just going to say, okay, we'll just shrink them down to be 1 centimeter on each side, and we're going to keep it here and solve for this numerically. So I'm going to go in here, and I'm going to start writing out that energy balance that we just derived. So I'm going to pick a cell that is not on the end. So it's not touching a boundary like these guys. I'm going to pick this guy here. So this would be our IJ cell. So I'm going to type in equals, and I'm going to start typing out this energy balance that we just derived here. So here I'm going to go minus K, and I'm going to use an absolute cell reference there by hitting the F4 key. So I got minus K, and now I'm going to refer to these temperatures. So here's my finite difference approximation. I have the temperature of this corresponding node. So this would be our IJ node, and here would be our I minus 1J node. So here's our delta T. I want to divide by delta X. I want the temperatures to be relative references, because ultimately we're going to copy this cell all over the place, and we want each energy balance to refer to the corresponding temperature cell. But we want anything that's referencing something from the far left-hand side, these constants, we want these to be absolute references. So I'm going to toggle that F4 key on my keyboard and get an absolute reference there. So here we have minus k dt, or delta t over delta x, and I'm going to multiply that by our cross-sectional area, which was delta y. I want that to be an absolute reference, and z, I want that to be an absolute reference. So here, so far, I'm going to just escape out of that cell for a second. So here you can see this term represents our x in term, and I'm just going to give myself, just to be organized here, I'm going to give myself a couple of spaces here for adding in my next term. So my next term is going to be the x out term, and that is similar. I have the plus k times my temperature difference approximation, so I'm going to go the I plus 1 cell minus the ith cell, so I have k times delta t. Here I want to divide by delta x again, and I'm going to multiply that by my cross-sectional area, delta y times z, and again I want both of those to be absolute references. Okay, so now I have this first term is my x in term, here's my x out term. Again, I'm going to put a couple of spaces, and now here's my y in term. So I have minus k multiplied by now my y temperature difference, which is going to be our jth cell minus the j minus 1 cell divided by delta y now, multiplied by my cross-sectional area. Alright, so this is my y in term, and then finally my y out term, and remember the out terms had a positive on them just because of the way that Fourier's law works. So here we have plus k times my temperature difference, which is now going to be the j plus 1 cell temperature minus the j minus 1 cell temperature, and I divide that by delta y, and now I get my cross-sectional area, which is now delta x times z. Alright, so now I have the four terms. I'm going to leave the generation term alone right now. So here we have the x in term, the x out term, the y in term, and the y out term. And because I did this with those absolute references in the right places, hopefully, I can take this cell and I can copy this over to all of these internal nodes. That same energy balance would apply. And what I want to do to check myself is use this nice feature of Excel where I can hover over the equation, I can click on it, and I can just make sure this particular cell, see how it gives us this little cluster of temperatures that it's representing. I want my cell to be in the center of the corresponding temperature cell with these references like that. And then I want the other references to still be the same constant. So it looks like we did that correctly. Let's just spot check another spot. So it looks like I'm referencing the same cluster. That's great. And I'm referencing the same absolute cells over here. All right, so because these are all internal cells that are not touching a boundary or a surface, they should all be uniform. Little trick, if we have constant surface temperature boundary conditions, so you notice I've created these rows and columns all along the outside, so we can use these to represent boundary conditions on our various surfaces. So if we have constant surface temperature boundary conditions, what we can do is we can extend this energy balance up to this cell here. So I'm going to hover over it, and now look, it's referencing a temperature that's outside of our control volume, but it's going to pick up the surface temperature boundary condition here. So the way I've set this up, it's actually safe to go ahead and use the same energy balance for these boundary cells. So I'm now just copying my energy balance to everywhere in there. All right. So now we've got 100 different energy balances set up, but these are all referencing blank temperatures. So let's give this some boundary conditions. I'm going to use Kelvin temperature for this problem. Celsius would be equally applicable. So let's say it has, let's say 400 is my boundary temperature. And what I'm going to do here is go to my formatting, and I'm going to just clear this for now. All right, so at this top boundary where y equals 0.1 meters, I'm going to assume that I have a surface temperature of 400. So I'm going to go ahead and do a paste special here and paste all those values. So the top boundary condition is that at y equals 0.1 meters, my surface temperature is 400. And let's use 300 everywhere else. So here on the left side where x equals 0, I am going to use a 300 Kelvin boundary condition, and I'm going to do that here. And I'm doing this paste special paste values so I don't mess up my formatting. Alright, so this is our system. If we had boundary conditions of 300, we're keeping the surfaces at 300 for all these three sides, but this side is at 400. What we need to do is, we're going to use Excel Solver here to solve for all these temperatures, but first we need an initial guess. So just using my engineering intuition, I know that everything in my system has to have a temperature between 300 and 400. So let's just use 350. So we're just taking a guess here so that our solver has an initial guess to start from. So I'm just going to fill in 350 as my guess initial temperature. And then if you remember, we set up all of our energy balances so that the left-hand side would have to be equal to 0. And that for this to be a real solution, the left-hand side has to be simultaneously 0 for every single node. And you can see that that is not the case. So we have zeros in a lot of places, but we have non-zeros everywhere else. So what we want to do is we want to solve these 100 equations for these 100 unknowns. So I'm going to go into my Data tab, Solver. I'm going to pick one of these cells, just any cell in here, and I'm going to say I want that cell to be equal to the value of 0. Here is where I change my variable cells. So notice that this says by changing variable cells. So I click here, and here I'm going to go define all of these cells to be my variables that I'm iterating over until my energy balances are solved. So when we go to constraints, if you don't have this in here, you would go to add a constraint. So now I'm going to say I also want every single cell, every single energy balance to converge. So I want every single energy balance to be equal to 0. I'm going to go ahead and use this GRG nonlinear solver, and I'm going to go ahead and hit solve. And so what's going to happen is that the solver is going to find the right combination of all 100 of these temperatures until all 100 of the energy balances are satisfied. So I go to solver, I hit solve. Solver is iterating here. You see this trial solution iterating. Oh, it says, oh, it found a solution. All constraints are satisfied. So I go here, I go over here. Yes, all of my energy balances are actually 0. And it has found this particular temperature profile. So looking at this numerically can be kind of a challenge. I mean, it looks, yeah, you do see these lower temperatures here, especially the further you get away from that 400 boundary condition. So this does look like kind of a temperature map. It's a lot easier to visualize, and here's a little trick if we do this conditional formatting. So I'm going to go to the Home tab, Conditional Formatting, Color Scales, and notice that I highlighted all of these temperature cells. Then I go to, Conditional Formatting, Color Scales, and I'm going to do this cold and hot color scale, this red, white, and blue color scale, so that it represents the higher temperatures with red and the cooler temperatures with blue. So if you notice, this actually looks pretty cool. So this is what our what our solution looks like. So this is an approximation of the heat equation. It's not continuous like you would get if you actually solved the PDEs of the heat equation, but it's a pretty good approximation where you have this resolution of each node is a 1 centimeter by 1 centimeter square. And just to remind ourselves, this is what we were looking at. We're looking at the temperature profile of a cross section of this beam here. And so in this particular case, we'd be perhaps heating this top surface so that it reaches 400, but then we're keeping these others cooler at 300. And if we did that, this is what our temperature profile would look like. So we can mix things up a little bit. So one thing that we can do, we can try some other conditions. So what I'm going to do is I'm going to introduce a couple of new boundary conditions. So let's assume that rather than having 400 constant surface temperature boundary condition here, instead let's assume that we have 0 flux here on the top surface. So the way that I can do that, I can go to all of these cells that are touching that top surface boundary, and we don't want these to be referencing the temperature here anymore. Rather, we want to let's just assume that that top surface is now very well insulated so that no energy crosses it. So if you recall, we would want to go to our Y, what we were calling our Y out term, which is here. And I can just put in a plus 0 there. So instead of conduction crossing that surface, we're going to have nothing. So we're just going to have a 0 there. You can also just delete the term entirely. So I've got this energy balance here on the top. I'm going to copy this over to all of the cells up here. So we now have a 0 flux boundary condition at the top. I'm going to couple this with a generation term. So let's say instead of a constant surface temperature being applied, let's say we have generation in, I don't know, let's pick one cell. Let's pick this guy right here, and let's add a generation term. So if you remember from our derivation, we had this volumetric generation term here. So let's apply a volumetric generation term there. So here I have my Y out term. I'm just going to leave the 0 in there. So I'm going to use this generation term. Here I'm using this 5 million watts per meter cubed. I want that to be an absolute reference. So now I also want that to be multiplied by my whole volume because it's a volumetric generation term. So I'm going to go dy multiplied by dx. Whoops. Okay, dy absolute reference multiplied by dx. Absolute reference multiplied by z. Absolute reference. Okay, so notice what that did to what's called the residual of my equation. It's like not close to 0. So I've already got my solver set up. Again, remember we have a 0 flux boundary condition now at the top. And I do want to double check these equations now. So if I go here, notice that this is no longer referencing that top temperature because the term that was dependent on it was the Y crossing that, the flux crossing that upper Y boundary. And I'll just spot check a few of these. So we're no longer referencing that temperature because we don't have a surface temperature boundary condition. We have a 0 flux boundary condition. And those, just spot checking, it looks like we're in good shape there. So I'm going to go ahead here and solve this again. I actually don't need to change any of the settings in solver. Those are just saved from before. But I do need to resolve so that all these residuals go to 0 and I have a real solution. So solver found a solution. So look, this is interesting. So we have here our cell that's generating gets really hot, and then you notice that energy flows away from it in all of these 3 directions. So the cell gets really hot. It doesn't have any way to escape this upper surface, so all of that heat has to flow from this node and then gradually outward. So we have this nice temperature profile. I'm going to call that good. I think you have some nice tools to solve now two-dimensional temperature profiles in a solid like this. Thank you very much for your time.